Most people associate ammonia with cleaners or smelling salts given its pungent smell. However, the use of ammonia in the making of these two products represents but a small fraction of the total global ammonia production. Ammonia is critical in the manufacturing of fertilizers and is one of the largest volume synthetic chemicals produced in the world. The global population would be at least 2 to 3 billion people less than it is today if not for the ammonia-based fertilizers and chemicals that have made a high crop yield possible. The most common method used for mass-scale ammonia production is the Haber-Bosch process. This process produces ammonia by introducing nitrogen and hydrogen into an enclosed chamber containing iron particles. By using high temperatures of up to 300 to 500 degrees Celsius and a pressure of 200 atmospheres, it is able to produce gaseous ammonia within the chamber. This hot gas mixture is then cooled into liquid ammonia in a condenser. However, since this process is extremely energy intensive and produces harmful waste products like CO2, it is necessary to explore different methods to produce this important chemical. That is why in this video we will look at how ammonia can be sustainably produced using nitrogenase. Nitrogenase is a complex that consists of the FEP protein containing gamma chains and the MOFEP protein which has 2 alpha and 2 beta chains. The MOFEP contains a P cluster which works in electron transfer and the FeMO cofactor which transfers nitrogen into ammonia. The FEP has 2 ATPs bound to it that work in conformational changes. The FEP with 2 ATPs bound can bind to the MOFEP which induces a conformational change. This gets the P cluster of the MOFEP closer to the FEP and the FeMO cofactor, which is necessary for the following electron transfer. The P cluster is now activated and an electron can flow from the P cluster to the resting FeMO cofactor, resulting in an oxidized P cluster and a reduced FeMO cofactor. This step is conformationally gated and was activated by the binding of the FEP with 2 ATPs. This model of electron transfer is called deficit spending, as after the intramolecular electron transfer, the P cluster has a deficit of 1 electron. Thus, an electron from the FEP flows to the P cluster to fill the deficit. This oxidized the FEP and reduced the P cluster again. Now the MOFEP and the FEP will dissociate. This is done by hydrolysis of the ATPs. The 2 inorganic phosphates that come from ATP hydrolysis are released, which is the rate-limiting step of the process. After that, the complex dissociates. FEP is now ADP bound and separated from MOFEP. This cycle has to happen multiple times as FeMO cofactor requires 8 electrons to reduce nitrogen to ammonia. Ammonia is a vital compound for the sustaining of global agriculture needing to be produced in large quantities. Current methods of production are effective in meeting demands but are detrimental to the environment in their required conditions. By using the nitrogenase enzyme as seen in the Azotobacter vinylandi bacteria, ammonia production is able to be done without the extreme temperatures and pressure that are seen in the Haber-Bosch process. This makes this method of production an environmentally friendly option. Thank you so much for watching.